Hello friends, let us now discuss the physiology of hearing. So the first thing in the physiology of hearing is binaural hearing. What do we mean by binaural hearing? Binaural hearing simply means hearing by two ears. Whereas we have monaural hearing. Monaural hearing means hearing by one ear, single ear. Now, what is the advantage of binaural hearing over monaural hearing? So, before we go to the advantages, let's look at this photograph. Now, I've already explained in the neural pathway of sound that sound from one cochlea over here, it goes to mainly the opposite side auditory cortex, but some sound also goes to the same auditory cortex. Right? Okay, so let's say this is the right cochlea, the sound is going to the right auditory cortex as well as to the left auditory cortex. Whereas we over here also have the left cochlea, and from here the sound is going to the left and the right auditory cortex. Okay, so that means each auditory cortex we can see over here is receiving sound from both the cochlea. Okay, now, so having understood this concept, let's go ahead and see the advantages of binaural hearing. So number one, we know, of course, we are hearing from the two sides, so we can hear the sound coming from the two sides. We can hear all the sounds. Whereas if we are hearing the monaural hearing, we are hearing only by one ear, we will be getting all the sounds from the one side. So directionality will be a problem. Why it's a problem? Let's see over here. Suppose this is the sound source. Suppose I have a sound source over here, it is giving me sound. Now the sound is reaching my right ear first. You see over here, the sound is reaching the right ear first, whereas it is not reaching the left ear. Why? Because the head is a obstruction. So you can see this left side has become a shadow side. Sound is not reaching the left ear. To reach the left ear, it has to first go strike a wall, reflect and come back. So by the time it will reach left ear, it has taken more time and the intensity has decreased. Okay, so right ear is receiving sound which is early, it has taken less time, it is early and it is high in intensity. Whereas the left side sound is late and it is low in intensity. Okay, so that means from both the sides, the sound we know go to each auditory cortex. And each auditory cortex is able to compare the right side sound with the left side sound. And it knows right side has come early, it is high intensity, left has come late, it is low intensity. And therefore, it will compare the sounds and it will tell you that this is the sound location. Sound source localization. So binaural hearing helps us in sound localization, and this is because of a phenomena that's known as head shadow effect. Okay, so that's known as head shadow effect. The head acts as an obstruction, creates an on side and a shadow side. So easy to remember, head shadow effect. Okay, now let me take you back to the auditory pathway. So we go back to the auditory pathway and we see over here the sound from the right side and from the left side is going through the brainstem into the auditory cortex. So at the level of brainstem itself, the sound of the right side and the left side is traveling together in the neurons. So the neurons of the brainstem, they are able to compare that right side sound is early and left is late, right is high, left is low, and it starts comparing the sound at the brainstem level, and that means the process of sound localization, it starts at the level of brainstem in the auditory pathway only. Okay, so this question is asked in the exam that the neural pathway of sound, the neural pathway of sound, what is it doing? We know it is transferring the sound. Anything else it is doing? It is comparing the sound of right side with left side. That means it is also doing a sound processing. It is analyzing the sound. So what is it trying to find out with this sound processing or speech processing? It is trying to find out what is the location of sound source. So sound localization. So the speech processing or the sound processing in the neural pathway of sound is concerned with sound localization. Right? This process of sound localization happens throughout the neural pathway and not just in the auditory cortex. Okay? Throughout the whole pathway, this process takes place. All right. Now, this we have discussed the directionality of sound. So we know that if we are hearing from both the sides, we can come to know that this bird is from on the right side, the plane is on the left side, people are speaking on the left side, the car is going on the right side. So we are able to find out which side, which object is, the sound is coming from which side because of binaural hearing. Can we do the same in monaural hearing? No. Why? Because if the sound is coming from only one side, from one cochlea, we have nothing to compare. We cannot say which side is early, which side is late. Okay? Whether the sound is high intensity or low intensity, we need to compare something. Okay? So monaural hearing, sound localization is not possible. Now we have to also remember that we are right now talking about sound localization in the horizontal plane. In case of vertical plane, whether the sound is coming from above or below, this vertical sound localization, this is mainly because of the shape of pinna. Okay, so remember the shape of the pinna is designed in such a way that the sound coming from each place, from above, from below, it is different. Right? So the vertical sound localization is dependent upon the shape of pinna. Right. Now let's look at something else. The sound is coming from the right side, the sound is coming from the left side, and the sound is there in the environment also. Suppose you have gone to a party, there is a background noise, and there are three people who are speaking to you, but you are interested in listening to only one of them. Can you listen to all one at this place? Yes, you can. You can concentrate on the speech of only one person and ignore the other people. You can ignore their sounds. How is this possible? Your brain, it's like a mega computer. So what it can do, it can take that person's voice of the right side and the left side, and it can compute and summate them. It can increase the intensity. Whereas other right side and left side, they are decreased, they are subtracted, so that is ignored. Yes, you go to a party, there is a background noise, there is a music, there is a DJ playing, and still you can talk to a person. You can listen to one person even when 3 or 4 people are speaking. So this helps you in a better hearing in the noisy environment, and this phenomena is known as cocktail party effect. So cocktail party effect is when you hear or talk to a person comfortably in a noisy environment. Okay, so that is known as cocktail party effect. Right. Now the sound is collected by the external ear and given to the middle ear. So the external ear also acts like a funnel, taking the sound and giving it to the tympanic membrane. The tympanic membrane gives the sound to the middle ear, which in turn transfer it to the inner ear. Okay, so let's understand the middle ear mechanics. How the middle ear is involved in this physiology. Okay, so the tympanic membrane is getting the sound, and it is vibrating and transferring the sound to the middle ear. What is the surface area of tympanic membrane? The total surface area is 90 millimeters square. But is the whole tympanic membrane vibrating? No. Some part is pars flaccida, that does not vibrate. The fibrous annulus is fixed to the bony annulus of EAC. It does not vibrate. So the effective vibratory area of tympanic membrane is only 55 millimeters square, right? And that means this is the area of tympanic membrane which is collecting sound, and it gives the sound to the ossicles, that is malleus. Malleus is attached to tympanic membrane. and the malleus transfers the sound to incus. Incus gives it to stapes. Now the stapes gives inside to the scala vestibuli through footplate. What is the surface area of stapes footplate? It is only 3.2 millimeters square. That means you are collecting sound at 55 millimeters square, not 90. 55 is the effective vibratory area. And you are giving the sound inside to the inner ear through only 3.2 millimeters square. We are collecting the sound at a bigger surface area, as we can see over here, and giving it inside to a small surface area. So per square area you are concentrating the sound, and that is known as areal ratio. Per square area the sound has been concentrated, or we can say the force has been amplified. How many times? 17 times. Okay, so the middle ear has amplified the sound with the help of areal ratio 17 times. 17 times the sound has been amplified. Okay, so do we have another ratio in the middle ear? Yes, we have. But before I take you there, let's go and look at this. So we have a couple. The couple has gone to a date. The date was in a children's park. What do we have in the children's park? We have a seesaw. So to do some time pass, they started playing a game of seesaw. But there was a problem. What was the problem? One of them weighs 50 kgs, whereas the other person weighs 100 kg. Now, can this 50 kg person lift the 100 kg person? Yes or no? In this lever, yes. This can happen. How? You see over here in this lever, suppose this length is x, we can very clearly see that on this side, this is 2x. Remember, torque. Torque is the rotational motion, the rotating force, and that requires force into length. So torque is force into length, rotational motion. That means if I increase the lever, I can decrease the force required. So this over here, the lever has been made twice, so we need only half the force required to cause rotation. So yes, this is equally balanced. The 50 kg person can lift the 100 kg person. Okay, now similarly, suppose I have this lever mechanism and I have over here a length of x, and this of course is 2x. Okay, and I have a weight of a over here. So similarly, let's say I have a lever over here of x and 2x, and I'm applying a force of a over here. How much force will I get in return? We all know now the answer. The answer is twice of a. We will get the double of force. Okay, now let's say I have a lever of x and 1.3 times x, and applying a force of a over here. The force applied is a. How much resultant force will I get? Now the answer is 1.3 times a. So this lever increases the force from a to 1.3 times a. Now similarly, we also have a lever in the middle ear. This lever is between the long process of incus and the handle of malleus. Okay, so handle of malleus and long process of incus. So let's say the length of long process of incus is x. You can see the handle of malleus length becomes 1.3 times x. And this over here is the fulcrum. Right? So suppose if sound force of A is given to the tympanic membrane and it moves the handle of malleus, how much force is transferred by the stapes inside? This will be 1.3 times A. So you see what has happened in the middle ear? The sound has been further amplified from a force of A to 1.3 times A, and this is known as lever ratio. So the middle ear, the lever ratio is 1.3:1 between the handle of malleus and long process of incus. Okay, so this lever ratio further amplifies the sound 1.3 times. Okay, so we have already seen that the aerial ratio sound is amplified 17 times. Both of them, they get multiplied, and the total amplification comes out to be 22:1. This is known as middle ear transformer ratio, also known as ossicular coupling. So what is the action of middle ear? It acts like a coupler, like a transformer. It is amplifying the sound 22 times. Right? Okay. Now, let's see over here in the tympanic membrane. What do you see? You see that the center of the tympanic membrane is attached to the handle of malleus, which is further attached to incus and then to the stapes. So it is not able to move freely. Whereas the periphery of the tympanic membrane is able to move freely. Which part? Periphery of pars tensa. Okay, so periphery of pars tensa, this is the most mobile part of tympanic membrane. Remember, when I taught you tympanic membrane, we discussed about the handle of malleus and we discussed about umbo. Okay, so we discussed about umbo. Umbo is the tip of handle of malleus, and there I told you umbo is the most mobile part of malleus. So remember the difference. Umbo is the most mobile part of malleus. It is in the center of tympanic membrane. But when we talk about tympanic membrane, the most mobile part is the periphery of pars tensa. Right? Okay. Now, because of this, an effect is created that is known as curved membrane effect or catenary effect or a catenary lever. Okay, because the periphery is vibrating more than the center, it increases the sound force by almost 2 times towards the center and helps in amplification. However, in considering all the amplification, this is very less, but yes, this has a minor contribution to the amplification of sound by the middle ear. Okay, so that is your catenary lever. Okay, any other function of the middle ear? Now let's see in this. We know that the sound travels fastest in solid. You know, the sound is a mechanical wave. It is a wave of contraction and rarefactions. Okay, the sound particles, they move like this: contractions, rarefactions. Now, because the sound travel is dependent upon the particles in a material, the sound does not travel in vacuum. Remember, it travels in air at the speed of approximately 340 meters per second. Okay, so exactly it is around 343 meters per second at the level of sea level. Okay, and then in the liquids, the sound may travel somewhere between 1200 to 1400 meters per second. In solid, this speed may go up to 4000 to 5000 meters per second. So sound travels fastest in solid. And what are ossicles? Ossicles are solid. So the sound that is coming from here, from the EAC, it goes to malleus, incus, stapes, these are solid. So this travel is very fast and it pushes the stapes footplate in. Now that means the perilymph is pushed in, and perilymph is a pretty non-compressible fluid. So this goes in and immediately through the helicotrema it pushes the perilymph in the scala tympani out, and the round window, it bulges out. Right? This happens very fast because sound travels very fast in solid. But we can see that from here some sound is also going through the air in the middle ear to the round window. But this sound is going through air. So it is late, it is slow. By the time it reaches the round window, the foot plate has already started coming back. So this sound further pushes the round window and it helps in foot plate coming out. So what do we see over here? When the foot plate goes in, the round window secondary tympanic membrane comes out. And when the sound reaches the secondary tympanic membrane, it pushes it in. At that time, foot plate is coming out, so foot plate comes out. Therefore, the two windows, they move like this. One is going in, the second one is coming out, the second one is going in, the first one is coming out. This is known as phase difference. The two windows are moving in a phase difference. Therefore, what happens? The sound goes in. The two windows helps in the movement of fluid. If both the windows, they move together, they will start cancelling out each other. So the middle ear creates a phase difference between the two windows that is also known as acoustic coupling. So there are two functions of middle ear. Number one, we have seen the amplification or the transformer ratio, also known as oscicular coupling. And the second is acoustic coupling, that is the phase difference. Now we see, let's say there was no middle ear. Let's say there was external ear and there was inner ear. Inner ear is filled with fluid. And let's say the sound directly strikes the inner ear without the middle ear. What will happen? The middle ear is filled with fluid. And when the sound strikes the fluid will reflect back the sound. Why? Because the particles of air, they move freely. Whereas particles in the liquid, they have more inertia. So it will take more force to move them. They will not move freely. Okay? It will reflect almost 99.9% of the sound away. Whereas this mechanism of middle ear, the tympanic membrane, the ossicles, they have taken the sound, they have increased the force, they have amplified it, and they have successfully transferred it to the inner ear by matching its inertia, by matching its impedance. So the middle ear mechanics helps in the impedance matching. It matches the resistance, the impedance of the inner ear and transfer the sound to inner ear. And this is being done by two processes which we have discussed, oscicular coupling and acoustic coupling. So remember, the middle ear is involved in impedance matching with the help of oscicular coupling and acoustic coupling. Right? So sound goes to the inner ear. From the middle ear, the sound has reached the inner ear. Now what happens in the inner ear? We have already discussed that the sound displaces the fluid in the scala vestibuli, and this movement immediately goes to scala tympani and pushes the round window out. That part we have already discussed. Now this movement also moves the basilar membrane. Remember, the cochlea is divided into three parts by the two membranes, resinous membrane and basilar membrane. Okay, and now the movement has moved the basilar membrane. What is there on the basilar membrane? On the basilar membrane, we have the organ of Corti. So we have already discussed the organ of Corti. It has two special type of hair cells, that is the outer hair cells and the inner hair cells. And they have hairs which are embedded in the tectorial membrane. Now there is a movement of the basilar membrane. This movement of the basilar membrane pushes the basilar membrane up. So these outer hair cells, they are also pushed up. Now they have hairs, and these hairs, therefore, which are embedded in the tectorial membrane, they therefore get bent like this. So they were like this, and now from here they have got bent like this. What is the significance of this? Let's look at the hair cell. So this is a hair cell, and you can see it has these hairs. These hairs are actually stereocilia. Okay, these are stereocilia. They don't move on their own. Now let's look at the structure of stereocilia. Let's go to a magnified image. So you see over here, we can see the stereocilia. Now these stereocilia, if you see over here, they are attached to each other. With the help of a tip link over here. So this link is like a spring. It is attached from one stereocilia to the side of the next longest stereocilia. This tip link, you can see it is made up of Catherine 23 and Proto-Catherine 15. And this tip link is attached to a channel that is a cation channel, a positive ion channel. Okay, it's a cation channel or a positive ion channel. This channel opens because of the mechanical force, and it is a cation, that means a positive ion channel. So it is also known as mechanico-electrical transduction channel. So that's a fancy name for a simple cation channel. On this cation channel is also attached a protein, that is your myosin protein, the same protein which is in the muscle fibers. Okay, so that's the stereocilia structure. Now let's see what happens, what is the importance of this stereocilia structure and the tip links. Okay, these tip links are very important. Alright, now before I explain the function of the tip link, let's look at a syndrome that is known as Usher syndrome. The Usher syndrome consists of sensory hearing loss along with progressive vision loss that is due to retinitis pigmentosa. And this Usher syndrome is because of the mutation of gene encoding cadherin 23 and Proto-Cadherin 15. So we can see the importance of the tip link because these are forming the tip links. Now this is in an autosomal recessive inheritance. That means both father and mother have to have the gene mutation. So it is generally confined to the Finnish population and people of Ashkenazi Jewish heritage. Okay, now let's look at these hair cells. So we can see the flask-shaped inner hair cell and the tubular outer hair cells. Now in both the hair cells, whenever the stereocilia move towards the longest stereocilia, there is depolarization. That means there is stimulation. And whenever they slack on the opposite side, there is hyperpolarization. That is, there is inhibition. What is the cause for this depolarization and hyperpolarization? Involved over here are the tip links. So as I already told you that these tip links, these are spring-like connections going from the tip of one stereocilia to the side of the next stereocilia where we have this cation channel. So whenever the movement reaches the basilar membrane and it moves the basilar membrane up, the hair cells are also moved up, and that leads to bending of the hairs like this. So what happens? You can see the tip link has been stretched. So when the tip link has been stretched, it opens the cation channel, the positive ion channel, and you can see the potassium ion and the calcium ion both going in. So there is a movement of ions. Okay, and what is this known as? This movement of ions causes electric current, a potential in the inner ear that is known as cochlear microphonics. Right? So this is known as cochlear microphonics. Remember, we have a potential in the inner ear that we discussed earlier, that was endocochlear potential. That was because of the sodium potassium ATP is pumped in stria vestilaris. It creates a positive voltage in the scala media as compared to the scala vestibuli and scala tympani. That was a DC potential. Now, cochlear microphonics, what is this? You see the positive ions are going in. Charged particles are moving in. So there is production of electric current. What is current? Movement of charged particles. This is known as cochlear microphonics. So this cochlear microphonics is a potential produced in the inner ear. Why it is produced? Because of opening of the cation channel. Okay, so this potential is produced because of opening of cation channel. And when has the cation channel opened? In response to sound stimulus. In response to sound stimulus. Remember, endocochlear potential is not dependent upon sound, whereas cochlear microphonics is dependent upon sound. Okay, now the outside the stereocilia was positive, inside was negative. But the positive ion are going in, so negative starts becoming positive and positive starts becoming negative. There is a change in polarity, just like an alternating current. So this is a AC potential. Okay, so cochlear microphonics is an AC potential. Okay, now remember, cochlear microphonics is mainly produced in the outer hair cells. All right, so this is mainly produced in the outer hair cells. Okay, although some contribution is by the inner hair cells, but because outer hair cells are much more in number, so it is mainly said to be produced by the outer hair cells. Now what happens when the potassium and calcium ions have gone in? Now you see, the calcium attaches to the myosin protein over here and it moves the myosin protein down. So the cation channel moves down, and as you can see, the tip link relaxes. And therefore, the hair comes back to the normal position. This stereocilia has moved back to the normal position. So therefore, the cation channel is closed and more influx of potassium stops. So the calcium which is going along with the potassium, it actually closes the door from where the cation channel is moving in. Right? Okay, so what has happened inside? Inside the hair cells, now we have more potassium. Okay, and this is therefore known as summating potential. So this is a potential which is generated inside the hair cells. Once again, it is mainly generated inside the outer hair cells, more than 95%. Some is also contributed by the inner hair cells. Okay, so summating potential, however, is a DC potential. There is no active transport of ions. So there is no change in polarity. It is a DC potential. Again, it is in response to sound, but it takes more time to come. What comes early is cochlear microphonics. So summating potential has a higher latency. Right? The summating potential has a higher latency, whereas cochlear microphonics has a lower latency. Latency means the delay from the stimulus. Right? So we have seen in this photograph the cochlear microphonics and the summating potential, and we have also seen that the sound, it moves the stereocilia and therefore causes an influx of potassium into the hair cells. Both the outer and the inner. Majorly the outer hair cells move. Now what is the role of outer hair cells when the potassium goes in? What will it do? You see, these outer hair cells, in the walls of the outer hair cells, we have a protein which is known as pristin. Okay, so we have a protein known as pristin. Now this is in the wall of the outer hair cells. This is a contractile protein. It can move and it can change the shape of the outer hair cells. It also has a voltage sensing capabilities. So when the potassium goes in, when the cation goes in and the anion decreases, what will happen? It will start contracting. So it will contract the outer hair cells, and therefore the movement of the basilar membrane is amplified. So it amplifies the movement of the basilar membrane. So therefore this is known as somatic electromotility. So outer hair cells, their response is at the level of the basilar membrane, they amplify the sound signal and they make sure that the sound signal reaches the inner hair cells. Right? Okay, let's look at this and see the movement of the outer hair cells. I've added a small music along with this video so that you can actually enjoy the movement of the outer hair cells.
1, 2, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're going to rock around the clock tonight. Put it to that right song. Join me home. Have some fun when the first night's won. Rock around the clock tonight. 12 o'clock, rock, rock, rock,
Okay, so that was an interesting movement, and that is how the functioning of outer hair cell is. Now, what about inner hair cells? The inner hair cells, as we can see, they are flask shaped, and as the stereocilia move away, and you see there is influx of potassium. So the same tipplings are there in the inner hair cells also. This potassium goes inside the inner hair cells, and it leads to movement of calcium into the hair cells. Okay, the calcium goes into the hair cells, and it attaches to the vesicles which have glutamate. So you see these glutamate containing vesicles, on attachment of the calcium, they fuse with the membrane and they release the glutamate. The glutamate goes to the afferent nerve ending and it causes nerve stimulus. Right? So there is generation of eighth nerve action potential. We remember in the nerve, the potential that is generated is always action potential. What do I mean by action potential? Action potential, there is a all or none phenomena. That means if the stimulus is below the threshold, we have a sub-threshold stimulus over here, there will be no response. Whereas if we have a threshold stimulus or a supra-threshold stimulus, in both the cases, we will have a complete response. So it's an all or none phenomena that takes place in the eighth nerve, the action potential common to all the nerves. So these are the four potentials that we have seen in the inner ear. I'll enumerate them once again. Number one I discussed was the endocochlear potential, a physiological potential. Number two, I discussed the cochlear microphonics. The third was the summating potential. And the fourth we have seen is the eighth nerve action potential. Now remember, the outer hair cells and the inner hair cells, in them, both of them have the tipplings. There is a movement of potassium inside. The outer hair cells, there is somatic motility that leads to amplification of sound signal. In the inner hair cells, that leads to movement of calcium and it stimulates the eighth nerve. So eighth nerve stimulation is majorly by the inner hair cells. Although some efferent fibers are also reaching the outer hair cells. So afferent are mainly in the inner hair cells. Some efferent are reaching the outer hair cells. They are actually coming from the superior olivary complex and they help in regulation of this neural pathway. Alright, so suppose we compare this summating potential with the eighth nerve action potential. So I put an electrode and I measure the summating potential and I compare with the eighth nerve action potential. What do we see? Normally, the summating potential is less than 30% of action potential. Or you can say that the summating potential to AP ratio is less than 0.3. However, in case of a patient of Meniere's disease, the summating potential is more than at least 45% of action potential. Or you can say SP to AP ratio is more than 0.45. So whenever it is more than 0.45, it is indicative of Meniere's disease, and this investigation is known as electrocochleography. It is used for the diagnosis of Meniere's disease. Right? Okay, remember this is an investigation which is good for diagnosis. The only problem with this investigation is that this is an invasive investigation. You have to insert an electrode by making a hole in the tympanic membrane and you have to place the electrode on the round window. Okay, so it is an invasive investigation as you are making a hole in the tympanic membrane. Okay, now there's another function of the inner ear which we call as frequency localization in the cochlea. Now, the human body is capable of hearing sound in the range of 20 hertz to 20,000 hertz. So, this is the frequency range we are able to hear. Now, this concept of frequency localization, it says that the 20,000 hertz is heard near the base of the cochlea or the basilar membrane where we have the organ of Corti, and the 20 hertz is heard near the apex. Okay, so that means each frequency has a particular location for it to be heard. So that was the place theory for frequency localization. Although this theory is no longer followed, but it helped us understand the concept of frequency localization. The correct theory I will inform you in some time. Now, what does this frequency localization actually means? It means that each frequency has a different place on the basilar membrane. That means 20,000 hertz is heard at the base, and we have the 8,000 here, we have the 4,000 here. That means each frequency of the sound is heard at a different place in the basilar membrane, and that actually means from each part of this basilar membrane a different neuron of the eighth nerve is coming out. That means each neuron is also getting a separate frequency of sound. That means the cochlea has successfully broken down the sound into different frequencies. All of us have seen the keyboard or the harmonium. So we know whenever we press a button, a key on the keyboard, what happens? Whenever we press a button on a piano or a keyboard, what happens? A different frequency of sound comes out. And when we combine all the movements, music is created. Right? Now, the cochlea has done exactly what is reverse is being done in a keyboard or a piano. It has broken down the sound into individual frequencies. Okay? Now, it is not the property of the cochlea or the basilar membrane. It is actually the property of the sound itself. How this frequency localization has been explained with the help of a traveling wave theory. Now, suppose in this traveling wave theory, we give 4 different frequencies of sound. 1, 2, 3, and 4. Okay, we give 4 different frequencies of sound. Now they make the basilar membrane move in a different way. Let's say this black line over here, this is the basilar membrane. This is the base, and this height is the apex. So we can see the 4 frequencies of the sound. They have moved the basilar membrane in 4 different kind of waves. Each wave has a separate peak. Now, peak is the place where a sound is maximum heard. That frequency is maximum heard at the peak. So that means these waves, they are maximum heard at this place. Okay, now what does this traveling wave theory says? It says as you increase the frequency of sound, this peak starts shifting towards the base. That means it starts traveling towards the base. That means the high frequency is heard near the base. Whereas as you start decreasing the frequency of sound, the peak shifts towards the apex. Okay, so that means low frequency is heard near the apex. This is known as traveling wave theory, and it was given by von Becquerel. Von Becquerel got a Nobel Prize in Physiology or Medicine for the traveling wave theory in 1961. All right, so this basilar membrane, it is narrow, it is thick and stiff near the base. Therefore, high frequency is heard near the base. Whereas it is broad, it is thin, and it is mobile, it is less rigid near the apex, and low frequency is heard near the apex. So that is your traveling wave theory. So actually the sound is able to make more movement in the basilar membrane at a particular time. So the sound is divided into different frequencies right at the level of cochlea. So what does that mean? That means the cochlea has divided the sound. Now the neural pathway is frequency coded. Each neuron is taking a different frequency of sound. You see, the sound from the cochlea, from the organ of Corti, is going by different neurons, and this neural pathway is now frequency coded. So this question is asked in the exam. How is the neural pathway coded? The neural pathway is coding. This neural pathway coding is done in terms of frequency. We have a high frequency neuron, we have a mid frequency neuron, we have a low frequency neuron, and this continues from the level of cochlea till the level of auditory cortex. Right? Okay. And what is responsible for this frequency coding? The traveling wave theory at the level of cochlea. So frequency localization takes place in the cochlea that we have discussed. Okay, and over here I would like to remind you that the sound localization is because of binaural hearing. And that question I have discussed earlier with you, that the neural pathway is also doing some kind of sound processing, which is involved in sound localization. The cochlea is doing a sound processing that is involved in frequency localization. So cochlea breaks the sound into individual frequencies and gives it separately to every neuron. Every neuron gets the sound from two-side cochlea and compares where it is high, it is early, or whether it is low intensity or it is late, and it does sound localization. I hope I am clear. Frequency localization cochlea, sound localization neural pathway. Neural pathway coding is in terms of frequency. Neural pathway speech processing or sound processing is for sound localization. Right? Okay. Now, sound has two properties. One I have just discussed with you is frequency. We can hear from 20 hertz to 20,000 hertz. Another property of sound is the intensity. The intensity is measured in decibel. Okay, let's look at the sound intensity. Remember, we are able to hear a wide range. At 30 decibels of the sound intensity, we are able to whisper. We are able to hear these whispers or the rustling of leaves. They produce a sound of around 30 decibels. The normal conversation is between 45 to 60 decibels. The background noise is around 60 decibels. You go to a marketplace, you go to some other music store, there is a background noise, it is around at 60 decibels. So therefore you have to shout, because your normal conversation is between 45 to 60, and if there is a 60 decibel sound, you want the other person to hear, you have to shout. Okay, now heavy traffic is around 75 to 80 decibels. It can even go higher. Okay, any sound above 85 decibel is harmful and it can cause noise induced hearing loss. Okay, a sound above 85 decibel is harmful. So over a period of time, if this sound is continuously given, it can cause noise induced hearing loss, acoustic trauma. A sound of 140 decibels or above, even if it is given for a few milliseconds, it can cause noise induced hearing loss. So above 85 can cause, above 140 or above will definitely cause noise induced hearing loss. So there should not be any exposure of 140 decibels or above sound. Okay, now there is a question which is asked in the exam: maximum audible tolerances. Now what is this question? This question, the maximum audible tolerance limit, has been set for the factory workers. Okay, and the factory workers, they work for 5 days in a week. How much is the maximum audible tolerance limit? The maximum audible tolerance limit has been set to be 85 decibel for 8 hours. Over here, I would like to clear a controversy. When India got independence in 1947, immediately after that in 1948, a Factory Act was given by the government. This Factory Act, which was formulated, is therefore known as 1948 Factory Act. Okay, and in that Factory Act, as per the WHO recommendation, the Indian government set a limit of 90 decibels for 8 hours. Remember, a normal factory shift is of 8 hours, so 6 hours options are anyways wrong. Okay, the normal factory shift is of 8 hours. So this was the limit set by the government in 1948. Later on, the WHO recommendation was to decrease this sound intensity by another 5 decibels. So the Indian government in 1994 created an amendment and modified this act, and thereafter the limit was decreased to 85 decibel for 8 hours. So this is the correct limit, and that can be verified by the Ministry of Labour website in the Government of India. Okay, so this Ministry of Labour, Government of India website clearly says that the Factory Act, although it is still named as 1948 Factory Act, but it had a lot of revisions and amendments, and the new value is 85 decibel for 8 hours. Okay, this value, however, is given wrong in lot of theory books as well as MCQ books because they have not yet updated the value. One more thing over here, what happens above 85 decibels? Above 85 decibels, if you give sound for more than 8 hours, patient is likely to have noise-induced hearing loss. So government has set a limit. There is a, as per the Indian government, there is a 5 decibel exchange formula. Okay, for every 5 decibel increase in sound, the time has to be reduced to half. That means if we increase it to 90 decibels, now the person can work for only 4 hours. There is a variability over here. The WHO still gives a 3 decibel exchange formula. So it says with every 3 decibel increase, the time should be reduced to half. So that is still variable as per the Indian government. It is still following the 1948 formula, but the WHO says 3 decibel exchange rate. Okay, however, the maximum audible tolerance limit is 85 decibel for 8 hours. And both the organization, the Indian government as well as the WHO says there should not be any exposure to sound at 140 decibels or above. Right? So this was the physiology of hearing that we have discussed. Now let us go to the next topic, that is the testing of hearing with the help of different audiometric and tuning fork tests. So this was the physiology of hearing that we have discussed. Now before we finish the topic, let's look at a video and have a quick recap of all that we have just studied. So we know that the sensory organ for hearing is the cochlea. This cochlea is a spiral structure. It is situated in the petrous part of temporal bone. Okay, so this spiral structure, it has around 2.75 turns or spirals around a central bony axis that's known as modulus. Okay, we can see the inner ear that has a central part known as vestibule, and from there we start the spiral of the cochlea around the central axis known as modulus. Let's take a cross section of the cochlea. So when we do a cross section, we can see that the cochlea is divided into 3 parts. The uppermost part is known as scala vestibuli, whereas the lowermost part is known as scala tympani. Both of them are filled with a fluid that's known as perilymph, which is high in sodium and low in potassium. The middle part of this cochlea is known as scala media. Okay, and this scala media has a sensory organ known as organ of Corti. Remember, the scala media is filled with a fluid that's known as endolymph. Okay, let's further magnify the organ of Corti. In the organ of Corti, you can see the tectorial membrane, you can see the hair cells, and it is resting on the basilar membrane. When we look on the hair cells, there are two types, the inner hair cells and the outer hair cells, which are arranged in rows. Inner hair cells are arranged in a single row, whereas outer hair cells are arranged in 3 to 5 rows. And they have stereocilia above them. Let's look at these stereocilia. Now, when we see the inner hair cells, you can see the 8 nerve fibers are reaching the inner hair cells and also the outer hair cells. But more than 95% of the afferent fibers, they are coming from the inner hair cells, whereas only less than 5% of the fibers, the efferent fibers, they reach the outer hair cells. These efferent fibers come from supraolivary complex and they help in regulation or modulation. Okay, now on these stereocilia, once we magnify them, we can see the special links known as tip links, which arise from the tip of one stereocilia and they go to the next higher stereocilia. Okay, the sound comes from the external environment, reaches the tympanic membrane, moves the tympanic membrane, which in turn moves the stapes footplate at the oval window. This movement of stapes footplate moves the round window out and a nerve impulse is generated that goes along with the 8th nerve. Let's look inside the cochlea. So we see inside the cochlea, the sound has moved the organ of Corti. It has moved the basilar membrane. On the basilar membrane, we have the organ of Corti. The organ of Corti, this is the resting position. It moves up, that causes depolarization. It moves down and it causes repolarization or hyperpolarization. This up and down movement creates a nerve impulse that is going along the 8th nerve. Okay, let's look at so this continuous up and down movement keeps on doing the depolarization and the repolarization, and sound continuously keeps on going via the 8th nerve to the auditory cortex. Now let's look at the level of stereocilia. You can see with this movement the stereocilia are going out and in, they are moving, they are bending. When they bend, they cause depolarization. When they again slide back, they cause repolarization. At the tip, at the level of stereocilia, there is a high potassium fluid. At the base, there is a low potassium fluid. So what happens when the stereocilia move like this? They are the tip links attached on the tips of these stereocilia, they are stretched, and that leads to opening of the cation channels. So potassium moves in and that causes your depolarization. This potassium goes down at the level of the base of the hair cell and it causes opening of the calcium channels. The calcium channel, they come in and they attach to the vesicle having glutamate. The glutamate vesicles fuses with the wall, releases glutamate that induces the action potential. At the same time, the potassium goes out through the potassium channels and there is repolarization of the hair cell. Okay, so there is a continuous movement of potassium into the hair cell at the apex causing depolarization, and there is a movement or the efflux of potassium at the base that causes repolarization, and that induces the action potential and the nerve impulse. Thank you.